Under which of the following is work done? Under which of the following is work done? Is equally an option. Under which of the following is work done? Work is said to be done. Work done is first times what? Distance. So these two must be present before you can say a work is done. There must be a force which moves a certain distance. If there is a force and there's no movement, work done is 0. If there's movement, there's no force. Work done is 0. Work is said to be done whenever a force moves a certain distance in the direction of the force. Are you getting it? If it is opposite, then work is still now done. Are you getting it? So work is said to be done when a force moves a certain distance. Are you getting it? In the direction of that force, then work is said to be done. So here, so the option says a man supports a heavy food above his head. A man supports a heavy food above his head. He supports a heavy food above his head like this, but he's standing still. Is there movement? No movement. Is the work done? No work done. So the second one is a boy climbs onto a table. So there's a table, then someone climbs the table. He climbs the table. Okay, so that one is very close. Let's see if it's the one. And then the third one says a man pushes onto a table. Okay, so someone push a man onto a table. Okay, and then another one is a woman holds a pot of water. So you hold a pot of water, there's no movement. All right, so a boy climbs onto a table, a man pushes onto a table. Okay, so when you are pushed, depending on the weight of the table and the weight of the person that is being pushed into the table, if the weight of the person that is being pushed to the table is greater than the weight of the table, then when you're pushed into the table, there will be movement. But we're not told that the weight of the man that is being pushed into the table is greater than the weight of the table, so that the table would equally move in the distance of the direction of push. We're not told, so you can't assume. Okay, so and you are now told that a boy moves. A boy has a weight. Are you getting it? And he climbs onto a table. Okay, a boy has a weight and he climbs onto a table. So which one is the answer? You have the answers to be equals to the boy that climbs the table. So when he climbs the table, he has his own mass. Are you getting it? And or his own weight rather, and it covers certain distance. Are you getting it? So this weight covers this distance. Then you have this work. Okay, the man that was equally pushed, we don't know if the man was actually just by the table. Are you getting? We don't know the distance that is covered. He was pushed into the table. He might still be standing just by the table. Are you getting it? But if the man equally covers the distance, then that would equally be a work done. Okay, so question number 8 now. Calculate the specific latent heat of vaporization of a steam of 1.13 times 10 of steam of 1.13 times 10 raised to the power 6 heat energy. If the heat energy is required to convert 15 kg of heat to liquid. Okay, so you have calculate the specific latent heat of vaporization. So you have your latent heat. This is question number 8. This question number 8 is under heat energy. So it's asking us the latent heat of what? Vaporization. All right. Latent is actually the heat required to convert a unit mass of a liquid. Are you getting it? Maybe a solid to liquid, or liquid to what? To gas. Okay, or even solid straight to gas. That is what your latent is, without a change in what? Temperature, please. Without a change in what? Temperature. So when you change a state of an object, a unit mass of an object, are you getting it? Without changing the what? The temperature, then we have latent heat. When a change in temperature is involved, we have what we call specific heat. So now latent heat can be latent heat of fusion or latent heat of what? Vaporization. You could equally have latent heat of what? Sublimation. So when you have latent heat of fusion, you have an object is, you know, this is the curve. Let me just try to draw this. So the curve of actually water curve, this like that, like that, like that, and like that. This is how it happens. So this is temperature. This is temperature. Let's say degrees Celsius, like that, and then you have the mass of object that is being. Let's say you have that. Okay, so you have here, let's say minus 4 degrees centigrade. That's when solidification starts. Okay, so here, from here to here, let me call this point A to point B to point C to point D, E, and going to F, like that. All right, so here the object is solid. Below this the object is, so that's why you have water would be solid, you know, ice water, cold ice water that you got, that's solid form now. So that solid form want to change from that solid form back to liquid form. Okay, so you have from here to this point there will be a change in temperature. Okay, there's a change in temperature between this point and this point, because point A is minus 4 degrees centigrade and point B is 0 degrees centigrade. Are you getting it? But from point B to point C, there's a conversion. There's a change of states that takes place, but you notice that there's no change in what? In temperature. So at this point you have latent heat. Okay, latent heat occurs here. Then from C to D as well, let's say here is 100 degrees centigrade. Okay, so from C to D there's equally a change in temperature from 0 degree to 100 degrees centigrade. Then from D to here there is some sort of stability, but there's a change occurring. Are you getting it? Latent heat equally happens here. Okay, so A to B you have specific heat, C to D you have specific heat, here to F you have specific heat. Then from B to C you have what we call latent heat, and then D to E you have latent heat. So when an object changes from liquid to solid, or solid back to liquid, you have latent heat of fusion. And then when you have an object changing from liquid form to gas, when a liquid is being heated, you know, to get to a point that after it begins to vaporize, escape into the space, convert into gas. Are you getting it? That point we call it vaporization. As a latent heat that requires for an object to change to that to change the state without the change in temperature at that point is what we call the latent heat of what? Of vaporization. Okay. All right, so that's about that. So we have the latent heat of fusion and latent heat of what? Of vaporization. All right, so my latent heat of vaporization of fusion is the energy per unit mass. You understand? Where the Q is equals to the, where Q is equals to the heat energy added while M is equals to the mass of the substance that is changing the state. Okay. All right. So the latent heat of vaporization is to be determined when Q is given to be Q in this question. Q is given to be equals to 1.13 times 10 raised to power 6 joule, and then the mass is given to be equals to 15 kg. Okay, so now my latent heat of vaporization using this formula will be equals to 1.13 times 10 raised to power 6 divided by what? 15. Okay, so you're dividing 11 by what? By 15. So you are going to have this to be equals to, that's 113 divided by 15. So you have this, if you do your calculation, you have this to be equals to 75.3 times 10 raised to power of 7.53 rather. You have 7.53 times 10 raised to power 4. Okay, so you can guess the unit of that, joule per kilogram. So you have joule per what? Per kilogram. Okay, so that is your number 8. Now question number 9. A cell of internal resistance of 2 ohms supplied to a 6 ohm resistor supplies current to a 6 ohm resistor. The efficiency of the cell is what? The efficiency of the cell is what? So you need to know something, that for every circuit, this is under current electricity. For every circuit, there is something that brings energy into the circuit, and it's something that takes energy from the circuit. Are you getting it? To the load. So the essence, when you create a circuit, you want to power something. Let's say you want to power your bulb. In this case, your bulb is the load. Are you getting it? And then you go and buy your battery. You put 2 batteries on cells together. Are you getting it? You connect your wire from one terminal. You put the wire on the other terminal, and then you put that to the bulb. Are you getting it? Now, what you require, all you require is to power the bulb. Then you bring in the cells. The cell supplies the energy. This energy will need to travel, are you getting it, to the load that it needs to power. So the guy that brought in energy into the circuit is what we call electromotive force. Are you getting it? And the guy that take energy from the circuit is called the potential difference. Are you getting it? So we have what we call EMF, that's electromotive force, and the potential difference. So electromotive force bring energy into the circuit. The potential difference take energy from the circuit to the loads that it needs to power. So what I'm talking about in essence is, let's say you have your battery like this, then you create you have a terminal here, you have another terminal here. You try to put wire into the both terminal, and then here you power your bulb. I just create a simple circuit now. Let's say, don't mind my drawing, let's say this is a bulb, the load that you're powering. So this guy supplies the energy, right? So the guys that bring energy here is what we call the EMF. That's electromotive force. Electromotive force. And then here you have potential difference. It's an electrical pressure that takes energy from one point to the other. So you have the potential difference. This takes energy from the circuit to that point. So you have EMF present here like that. So your EMF has a formula which is equals to your V. This is denoted by V, and most of the time you see this being denoted by E, or you can write it complete. Is V plus IR. Are you getting it? Where R, this small r, is your what? This small r is your internal resistance. All right, that's your internal resistance. Okay, so now your voltage itself, which is your potential difference, we call it, is your I times R, where R is because of the resistance itself. I is the current. Okay, so your E becomes high R plus high small r, which is equals to, I is common, you can take it outside. You have this one to be R plus what? Small r. That is your electromotive force. EMF is equals to I into R plus what? R. That is your EMF. Okay, now your efficiency, you want to know if something is efficient. How the internal resistance is introduced, the power that is come in, that is delivered into the circuit, might not be exactly equals to the power that leaves the circuit because of the internal resistance of the material used. Are you getting it? So when you're calculating the efficiency, you want to know, compare the energy that came into the circuit to the one that left the circuit. Are you getting it? So you have the efficiency equals to the energy delivered. Let's say energy received, if you call it, or divided by the energy delivered times 100. Energy received, that's at this point, then the energy delivered from this point. Okay, like that. So now my or you call it power delivered if you like. So your power is high V. Are you getting it? So your power, the formula for your power is high V, which is same thing as high times V is high R. Abi, I told you now, which is same thing as I square R, which is same thing as V square over R. Are you getting it? This is power is equals to IV is equals to I square R, and it's equals to V square over R. If you do your because from here your R will be equals to I square, like that. So you can bring that in, so you have that to be that. Okay, so you have E, the efficiency now, the power delivered is equals to I square R divided by the power received, then divided by the power delivered. So that one is going to be equals to I square R plus R. Okay, so here you are going to have it times 100. So this is going to be R over R, because this cancels this, over R plus what? The small r. So here we are giving internal resistance R to be equals to the resistance itself, 6 ohm, and then the internal resistance small r to be equals to 2 ohm. So your efficiency is equals to R 6 all over 6 plus 2 times 100. That is 6 all over 8 times what? 100. So 8 times 7, 54. So you have this one to be 7, then it's remaining 2. So 6 rather. So you have 75%. So you have the efficiency to be equals to 75, approximately 75%. Okay, so that's your take.